So let's continue. So we have defined R bar like this. And what points are added to R? Well, the procedure is the same. As I said, if W Z is a complex number, then size cannot be 0. So W the new points in X correspond to a point with 0 first coordinate. Namely, when Z is 0, it is a new. So the complement of R in R prime is that's satisfy this equation with this equation. So put 0 here, and we obtain such a simple equation. Namely, we have 2 points in the complement of R prime, plus or minus square root of A. Recall that A, the overall constant, is not 0. So what we constructed is essentially R, and we added 2 infinite points. Well, this means that we describe this point in the coordinates of W prime. So what is this? Well, we have already mentioned that R prime is a non-singular one-dimensional complex manifold. So these new points, these infinities, are non-singular points. Namely, we can take a local coordinate neighborhood around each of these points. And so we obtained a non-singular compact Riemann surface, or one-dimensional complex manifold. Then, what is the shape of this Riemann surface? I mean, when we consider the Riemann surface for such a function, we glued 2 sheets by reverting the orientation of this sheet and we obtain essentially a cylinder. In the case of the Riemann surface for this, we also obtained such a description as we discussed today here. Well, then what is the shape of the compactification? Well, let's see. When the first, let's assume that these four complex numbers are not zero, and let's the inverse of those numbers, beta I. Then, as we saw here, our prime is a Riemann surface of such a function. Namely, it's the Riemann surface of such a function. So we can construct such a Riemann surface by gluing two sheets. By just identifying alpha, beta, z, and xi in this one. So this is R prime, and we have R. It's constructed in this way. But here we have identification, except at zeros and infinities. So from these two sheets, we have P1. From these lower sheets, we have another P1. And what we obtain is the union of two P1s with punctures at those roots of pi. And after that, we add those points, namely, well, except for these infinities, we have R. Here we have infinite plus, infinite minus. And adding infinities first to the sheet C plus and C minus will obtain P1 plus and P1. And we have the group there. But what is this? This is P1 with two cards. Let's open these cards like this. Like this. Then, well, as we have constructed the Riemann surface of R for Riemann surface of this equation in this way. We can construct the Riemann surface for compactification of the Riemann surface of square root of phi by gluing these two cylinders. What does this mean? This means that we have a torus. So this compactification or adding is obtained by adding two infinities. And actually it is a torus. So here we assumed for simplicity that there is no alpha zero among alpha i's. Because we want to invert alpha. And actually, even when there is a zero among alpha i's, it is almost the same because when alpha I, for example, alpha zero is zero, then R prime is defined by this equation. And since alpha zero is zero, it is nothing but the Riemann surface for this third degree square root of this third order polynomial. And well, this means that and in this case we contract the Riemann surface by gluing two such sheets with such cuts. But just identify infinity with zero. So this is in W5. This is in W, but here we have then The construction here does not change. Just in this case, so infinite in this picture corresponds to some point where psi is 0. And from this, we have again two P1s with two P1s in this way. And these alpha zeros or 0 is alpha 0 is identified with infinity in this picture. So again, this construction by doing two P1s can be applied. And from this, we have again tools. So we constructed R-bar compactification as a torus. And this torus has a name, elliptic curve, because we obtain, or we need it for the elliptic integral. Well, you don't have to. Well, I don't have to mention this for you, but sometimes it might, this name might cause confusion. This is not an ellipse, of course. This is essentially defined by this degree 3 or degree 4 equation. And when degree 5 is greater than 4, then the compactification of the Riemann surface for the square root of phi is called hyperelliptic curve. Of course, there is no hyperellipse or something like that. Maybe we should put parentheses here. It's a hyper of elliptic curve. And well, hyperelliptic curve has almost the same. Yeah, well, share many good properties with analytic curve, but well, we don't use it here in this course. And moreover, well, I always assume that up to here we assume that degree of phi is 4, and abruptly here appears degree 3 polynomial, Actually, everything is goes through, and yeah, if we replace beta and alpha here, you might see that the construction of the curve for degree 3 a polynomial is exactly the same as before. And moreover, when we classified elliptic integrals, we reduced the polynomial phi into this form by using personal linear transformations many times. Actually, the same is true for elliptic curves. We can use such a personal linear transformation for each sheet and reduce the polynomial to this case. Okay, I'll recall that this is this fractional linear transformation gives isomorphism of P1. So essentially, this transformation moves 4 points, alpha 0, alpha 1, alpha 2, and alpha 3, or maybe infinity and alpha 1 and alpha 2 and alpha 3 to any point to some another coding form. And as we saw in the proof of the classification theorem, we can choose for such points down to plus 1 plus k inverse minus 1 minus k. Or even when one of them is infinity. Or we can say that any elliptic curve can be obtained by compactifying such a Riemann surface. Okay, well, this is what I already explained you. Namely, when one of the when the polynomial is of degree 3, then we have the Riemann surface for such a polynomial, square root of such a polynomial can be obtained in this way. In other words, it's a P1 with two parts, one of which has infinite length. And they are good to a torus. So when the degree is 3, we have another torus. But essentially, this is the same. We can reduce the theorem to this case. And well, yeah, if you like, in this case. Okay. Any questions so far?
Yes, I have a question.
Yes.
And at the beginning of the lecture, there was a construction of compactification of the Riemann surface for the case of
This one, right?
Yes.
Sorry.
When the degree of phi is 3.
Yeah. We embedded it to P2.
Yes, and is it true that the result coincides?
We used another compactification, and are they the same or
probably? And then we used this compactification for the case of cubic polynomial as well. And so we have two compactifications of
that's a very good question. Thank you.
For degree 3.
Mention about that. Yes, probably you see that even when degree is 3, the construction in this way is can be applied to that case. Well, yeah. In that case, we have degree. Yes. Degree 3 polynomial. So this factor is absent. And we can obtain actually the same Riemann surface, and we can construct the isomorphism between the compactified Riemann surface, which we obtain here in P2, and a Riemann surface, compactified Riemann surface in this set, in this way. And well, yeah, actually the isomorphism is not very illuminating form and a little bit complicated. So I didn't mention it. I don't want to write it explicitly. So, well, yeah.
So they are isomorphic, but not immediately.
Yes, exactly.
Okay, thank you.
Since probably among you are those who are familiar with algebraic geometry, and so you would say, why don't you want to use the standard technique, right? Well, this is the very standard compactification in algebraic geometry, if you know algebraic geometry. And what we want to use is actually this compactification, which gives us a non-singular algebraic curve. So I could have started from this non-singular compactification, but well, for as well, the most that compactification I just mentioned, this P2 compactification. And yeah, what is important afterwards is actually the most important thing is this thing. We are gluing two P1s with two cuts. That is the most important thing among which I talked.
Okay, it's clear.
Okay, thank you. Any other questions? So, yeah, probably, yeah, we are almost out of time. So, let's finish today's session now. Well, I'm not sure whether we would have a normal course next week. Anyway, we probably will have another session next week, but I'm not sure. Please be informed later. Yeah. If there is no course next week, I shall tell you. If there is no announcement from me, then there will be. Okay.
Okay.
So I stop recording.